This is Robert from Microchip Technologies. Today I'm covering the basics of integrated op-amps on microcontrollers. At the end of this video, I will show a brief demonstration of using MPLAB Code Configurator to set up the OPAMP peripheral in seconds. First, let's ask, what is an op-amp? The operational amplifier is an analog integrated circuit that is designed to amplify the difference between its inputs, non-inverting, positive, and inverting, negative. Operational amplifiers are commonly used in everything from analog feedback loops to signal amplifiers. In terms of op-amps, there are two different types, discrete and integrated. A discrete op-amp is a dedicated analog integrated circuit, whereas the integrated op-amp is created on the same die as a digital device, in this case a microcontroller. The differences between these two implementations can vary greatly depending on which devices are being compared. Generally speaking, discrete op-amps have better analog performance and can have the ability to run on bipolar power, whereas the biggest benefit to the integrated op-amp is the reduction in the number of parts, the flexibility in configuring the op-amp, and the greater part density that can be achieved. Microchip produces both types of op-amps. For applications that require a discrete op-amp, visit us at microchip.com/amplifiers. The rest of this video will focus on the integrated op-amps in PIC and AVR 8-bit microcontrollers. The use cases for the integrated op-amps generally fall into three categories: signal processing, peripheral enhancement, and analog control. One of the biggest applications of the integrated op-amp is to condition analog signals before sampling them with the ADC. Inside most ADCs is a sample and hold capacitor which must be charged with the signal to be measured. The more impedance in series with the signal, the slower the capacitor is charged through the RC network. Another common issue is where the input signal is not sized to the input range of the ADC. When improperly sized, the resolution of the signal is not optimal since some binary codes will never be reached. The integrated op-amp provides a space-efficient method of buffering and scaling the input signal, which can improve signal acquisition time and resolution. Another use case of the integrated op-amp is as an enhancement to an existing analog peripheral on board. For instance, the output of an onboard DAC could be tracked and scaled by the op-amp or used to create a buffered copy of the signal from an unbuffered DAC. Finally, the op-amp can be used as a part of an analog control loop. As mentioned earlier, the op-amp tries to null its inputs to a differential voltage of 0. This effect can be utilized to create control loops for analog circuits. One such application of this is in a linear power supply. One of the biggest benefits of the integrated op-amp is its configurability. The microcontroller can configure and control parts of the op-amp circuit for design flexibility. To simplify the development process, both MPLAB Code Configurator and MPLAB Start provide a graphical user interface to set up the integrated op-amps in the appropriate configurations. Then, an API is generated to simplify control of the op-amp and other peripherals on the device. The flexibility of the integrated op-amp allows designers to create highly integrated mixed signal solutions. The op-amp can enhance the analog performance of the microcontroller while minimizing changes to the bill of materials or to the footprint of the design. The op-amp is also complemented by other analog peripherals on the microcontroller and the easy-to-use development tools. The next video in this series will focus on the op-amp peripheral in the new PIC 18Q41 and AVR DB product families.